Pumping! Initial talk, intendone, functional programming without a functional language. The talk functional programming without a functional language will start now in the tendone called Mickey Mouse. Okay, so we can press record, I guess. Ah, already started. Ah, that's great. So it's an honor and a pleasure to introduce you our next guest. She's Meredith Patterson. You probably already know her, and she's here for her honeymoon, right? So thank you for coming.
It's been great.
And so here you are, Meredith Patterson.
Thank you, everyone. All right, so quick show of hands here. Who speaks C? Okay, that's good. If you don't, this talk hopefully won't be too awful. There is a lot of C in it. I'm also going to try to speak slowly. So if I'm speaking too fast, please.
Sorry, that's because I have something to do with feminism.
As if. No, we will talk about all about the properties of functional programming in just a moment. All right, so just a quick introduction of who I am. So I studied linguistics in university, and when I moved on into the programming world, I started applying principles that I had learned about formal language theory, which is a subfield of computer science, to problems of security. How do we? How does the way that we implement protocols, implement message formats, implement data formats? How do the ways that we take shortcuts end up producing insecurity? So most of this ends up boiling down to parsing. When you're taking input from an untrusted source, you have to interpret it, and the rules for interpreting a protocol or some other format are described as a grammar, or at least can be, and in good protocols they are. So, what do we mean when we say a functional language? So if you're familiar with languages like C, you're used to procedural programming, where every instruction that you give is usually an instruction to change the state of some variable, change the state of some memory, change the state of some output device. But in functional programming, we do our level best to avoid that, except where it absolutely has to happen, like turning a LED on and off or something like that. The reason that we try to avoid mutable state is that when it's possible, so first of all, when a program is carrying around a lot of state, if a bit flips, or if someone manages to introduce a malicious piece of data, if the internal state of your program becomes inconsistent, undefined behavior might happen. Another thing that functional programming languages tend to do, instead of having for loops or while loops, you'll use recursion to iterate over, to iterate through lists or maps. They also typically allow you to use functions themselves as arguments. And you see this in you'll see this in some languages that are mainly procedural, like Python. you can pass a function as an argument. Normally you can't even do that in C because a function is its own special thing and it's not normally something you can pass as an argument, but we have a way to get around that we'll talk about later. Probably the core concept, though, of functional languages is that what they call a variable really isn't. There's this concept called referential transparency, where once a value is assigned, it stays that way. And of course, C gives you mutable state. There is really no such thing as a set it and forget it variable in C. So, in order to get around that, particular flaw, we have to program in such a way that, you know, once something is assigned, we just don't change it. And so the goal here is to use a procedural language in a way that appears on the surface to be more limited than the full power that you would normally expect, but paradoxically, what you end up with is much more predictable and therefore much more secure code. You end up with code that isn't going to surprise you. Okay, so when we have some input that we need to handle, we parse it, and that turns the raw bytes into objects of some type that we know what they are. Maybe that's a primitive type, maybe it's a struct. You know, in Java, of course, it's going to be an object. But, excuse me, whatever the case, if it takes a stream of bytes and it turns it into objects, that's a parser. The reverse of this, serialization, is when you already have a well-typed object and you want to send that to something else. So you marshal that out to a stream of bytes, and that can be reconstructed by some other parser somewhere else that can then understand what those objects meant. Taylor Hornby made this observation almost 2 years ago now, and it still holds true. Crafted inputs are the way that exploits happen. A vulnerability is sitting there waiting for some crafted bit of data to make the program in which the vulnerability exists do something that nobody expected. You think that it's your program slicing and dicing and doing all kinds of things to data, but no, the data is actually ordering your program around. So in language theoretic security, we have a few slogans. One of those is full recognition before processing. If you have like some input format and you parse a little bit of it, do something with what you just parsed, parse a little bit more of it, do something with what you just parsed, etc., etc., etc. It looks efficient, but the problem with that is if you've got other logic interspersed, what happens if you've parsed a couple of things and then all of a sudden the next piece of data that you parse gives you an error? What happens to all of the state changes that you made after you parsed those first couple of bits and performed the operations that were interleaved with them? Are you going to roll that back? It turns out to be much simpler and much safer to do all of your recognition up front. Once you know that you have valid data to work with, then do something with it. Beyond that, I mentioned earlier that for every input language, there should be some grammar that describes it. Moreover, if you're implementing something that has a grammar, but your implementation doesn't explicitly implement the grammar, your implementation is wrong. There will be an error in it somewhere. And we have discovered this with everything from, X509 to LD metadata. I mean, there's when implementations don't implement what they're supposed to implement equivalently, and they try to communicate with each other, they end up confusing each other. endpoints of computation need to be equivalent if you expect consistent behavior. And, you know, we've seen these kinds of problems in things like Heartbleed. You know, there was supposed to, the heartbeat packet was supposed to have a, there was a length field that specified how long the payload was supposed to be, and therefore how much data the responding machine was supposed to return. And it turned out that if you sent out a heartbeat packet with a very long value in the length field, and then only a couple of bytes of data, you could get the machine on the other end to regurgitate just whatever it had sitting in memory for however many thousands of bytes you asked for. You know, again, this is a parsing error. If the receiving machine had instead said, wait a second, that length field and the length of the payload don't match, I'm not going to answer this, Heartbleed would not have existed. You know, similarly, Shell Shock, Ghost, you know, even Image Tragic. Hopefully the days of named vulns are behind us, but these are all parsing vulnerabilities when you get right down to it, and we don't really see the flood of parsing vulnerabilities ending anytime soon. Excuse me. So, let's talk about some principles of logic that that we want most programs to have. So, for a sound program, you ask it to compute something, and whatever answer it computes for you, that answer is true. If the program lies to you, or even if the program is just wrong, it is unsound. There's also a property called completeness. Provided that there is an answer for some input, if you try to compute the if you try to compute the response to that input, you will actually get an answer. You know, if you don't get an answer, then it's incomplete. And probably most importantly, believe it or not, for our purposes here, number one, we want every execution to terminate. You know, we don't want to get stuck in an infinite loop somewhere. We want to make sure that we get one true. We want to make sure that we get one correct answer for every input that we could possibly submit. And you know, for many of those inputs, for invalid inputs, the answer is going to be no, reject it, knack, however you want to describe it. Okay, so let's take a quick tour through the various kinds of parsing algorithms that exist and what kinds of inputs you would want to use the different algorithms that exist for. So this diagram is a hierarchy of language classes. If you've ever had an automata theory class in university, you might recognize something like this. So the simplest languages that we ever deal with, okay, there's one even simpler than this called the finite languages. Like if you have a set of strings and that set is finite, that's actually a language. But it's so easy to deal with, you know, because you could just use a lookup table that we don't bother with it in this diagram. Regular languages can be infinite. But this is exactly the class of languages that is described by the regular expressions. And we're not talking about PCRE regular expressions here. There's no recursion allowed in the regular languages. So, you know, old school, like, you know, POSIX non-PCRE regular expressions. If you do admit recursion, if you allow rules to refer to themselves, then you have what's called a context-free language. Context-sensitive and recursively enumerable languages correspond to the linear bounded automata, which is basically a Turing machine with a finite tape. The recursively enumerable languages correspond to Turing machines. So you really don't ever want to have an input language that is recursively enumerable, because the parser that you would have to write for it would be so complex you wouldn't ever be able to verify it. You wouldn't ever be able to be 100% sure that it's actually correct. Okay, so let's talk about different kinds of parsers and what classes they're good for. So probably the oldest and simplest ones we have are called recursive descent parsers. There's this wonderful little tutorial called "Let's Build a Compiler" by Jack Crenshaw. It's free on the internet, and he teaches you literally how to write a compiler for a language that's kind of like Pascal, but you could apply this to you can apply his techniques to writing a compiler for any other language. And conceptually, it's incredibly simple. You have basically a tree of rules that can apply at any step of input consumption. You're matching on them and recursing down through the tree, trying to build up a parse tree that corresponds to the input that you've created. However, they do have some downsides. Unfortunately, recursive descent parsers can't handle left recursion. So if you have if you need some recursive rules, like to in order to describe, like, any potentially infinite list, that needs to recurse, and you have to write it right recursively. This isn't like impossible, but it can be kind of annoying and difficult to read sometimes. And the other problem with them is that because it's stupid recursion, there's no memoization, there's nothing done for efficiency. Occasionally the runtime blows up to exponential. But the good news is they can parse damn near anything. Okay, so parsing expression grammars are an improvement on the recursive descent parsers that are always unambiguous. This ends up kind of paring away some of the types of languages that you can parse. You can parse really complex things with a recursive descent parser. You're basically limited to a subset of the context-sensitive languages with parsing expression grammars. But the good news about that is that the subset of the context-sensitive languages that it does includes most network protocols. Like pretty much anything that has TLV fields, type length value, or just length value fields. You can handle that with a parsing expression grammar, and that's most network protocols, so that's handy. That said, you still can't do left recursion with them, so that kind of sucks. So then in the early 2000s, Brian Ford, who I think is now at Lausanne in Switzerland, came up with the idea of a Packrat parser. And Packrat is basically a parsing expression grammar with memoization. So it avoids that exponential blowup from that you see in the recursive descent parsers, because it remembers matches that it has successfully made before, and so it doesn't have to go and reparse things if it has to backtrack. It just goes and looks them up in the table that it built when it memoized things. And also, there are versions of the Packrat algorithm that can basically handle left recursion, except for some really weird indirect cases. Unfortunately, nobody really agrees on what the right approach to do is, and theorists are going to keep arguing because they're theorists. That's their job. Okay, so let's move down the hierarchy some. So let's get into the context-free languages. LLK is one of the oldest algorithms that we have for handling context-free languages. It is inherently left recursive. That's why it's called LL. LALR, which was invented by Don Knuth, is a right recursive algorithm. So if you have a If you have a grammar that is not convenient to write left recursively, but you can write it right recursively, use LALR. If it's easier to write it left recursively, use LLK. The K there means how many tokens of look ahead do you have? How many characters can you look ahead when you're making a decision? So in practice, there's like LL1, LL2, etc. So there's also GLR, the Generalized Lr Algorithm, which is it's LALR's younger brother. And the interesting thing about GLR is that in the case where your grammar is ambiguous, if there might be more than one way to successfully parse an input string, GLR will give you all of the results that you could possibly get. LALR will just give you the first one it finds. And so for regular languages, the NFA to DFA algorithm is probably the best thing going, because one problem with PCRE regular expressions is that because they're actually context-free, occasionally you have a pathological runtime. You'll have some string that causes PCRE to freak out, and it takes forever to return a result. If you're interested in how the NFA to DFA algorithm works, I highly encourage you to check out Russ Cox's series of articles online. He's got a couple of articles like just getting down into the guts of the Thompson regex VM. This is like Ken Thompson of Bell Labs, and explaining how all of that works. Okay, so the rest of this talk is mostly going to be about Hammer, which is a parsing library that my husband and I co-authored, and we specifically wrote it because we had some binary formats that we needed to parse, and nothing that was already on the market really does it well. Because for one thing, at least at the time that we started this, all the parsing libraries and tools that were available were byte oriented. They would consume input one character at a time. And that's fine for most text-related purposes, but what do you do if you're dealing with a packet format that subdivides a single byte into flags or like 2-bit chunks? That turns out to be incredibly difficult to do in something like Bison or Antler. Also, some protocols are douchebags and have varying endianness. TIFF, for instance, has a couple of magic bytes at the beginning that tells you whether the rest of the image file is big endian or little endian. I don't know whose idea this was, but it's a nightmare to implement, and there was nothing out there that could do it. So we had to actually figure out how to solve the problem of, okay, you have an input stream. Which end do you read the stream? Which end of the byte stream do you read it from? Okay, now which end of each byte do you read bits from? Because some things actually change this up. I want to say it's gzip that has you reading from that has you reading the stream from one direction, but the individual bytes in the stream from the other direction. Am I right? Is it gzip? Okay, cool. All right, I couldn't remember. It's been so long. Okay, so I mean, Bison, it turns out you can do a lot of, you can force Bison to do lots and lots of things if you're really determined to do it. But part of the problem with trying to make Bison do things it was not designed for is that Bison was only really designed for writing compilers or interpreters with. It's also, Bison is a code generation step. It generates parsing tables from the grammar specification that you give it, and when it's and as it's generating the parsing tables, it will tell you about ambiguities that it sees where these are called shift-reduce conflicts, and they can be very, very difficult to debug. And moreover, there's just still no good way to do bit fields in Bison unless you want to write lots and lots of semantic actions, and you're fortunate enough to be dealing with a protocol where everything is byte aligned. If you're dealing with, say, base 64, sorry. Okay, so let's talk about the principles of design that went into making Hammer. So we wanted to make sure, first of all, that this was that Hammer would be a library that would not create more confusing state than it took away. If the point is to minimize state, then you want thread safety. You want reentrancy. You don't want to have like one thread being able to muck around in the state of other threads and mess things up there. We want an API that people can that people can understand easily. Because you never want people to have to fight the tools you write. POSIX compliance was, mainly just because we're kind of anal about that. And moreover, we wanted it to be fast so that people would use it, and we wanted it to be correct so that it wouldn't screw people over. So, C turns out to be a terrible language for achieving most of these things because C has a lot of deficiencies. First of all, C has a really weak type system. C, the language that brought you type punning. Functional languages like Haskell or Scala tend to have really strong type systems. The compiler will figure out if you're trying to contort data into the wrong struct shape. But even if your language doesn't have a very good type system itself, you can still define the types that you want to work with, and as long as you reason about them, as long as you reason about them more strongly than the compiler does, as long as you're correct when you're doing that, you can actually you can give yourself the type system that the language doesn't give you by itself. Okay, so C doesn't let you use functions as first-order data, like we talked about earlier, and this is pretty necessary if you're going to be working in the functional style, because a lot of what the functional style involves is composing functions into larger operations, and if you can't pass functions around as arguments, what are you going to do? Well, you cheat and you pass around function pointers, and you do a lot of dereferencing behind the scenes, but you build your API so that the user never has to think about that. Okay, I didn't talk about strict and lazy evaluation before because functional languages can be either strict or lazy. Strict means that as soon as a value comes into scope, it is evaluated, if it can be. Lazy means that values will be evaluated on an as-needed basis. Probably the classic example of this is the infinite list. In a strict language, if you need an infinite list, well, you'll be waiting for a very, very, very long time for that list to actually be available for you to do anything with, because the language tries to actually create an infinite list, and eventually the killer gets you. In a lazy language, however, you can totally have lazy infinite lists, because when you ask for some item in the list, the language goes and computes it for you and hands it to you. So you can just pluck values off you can just pluck the head off of the list over and over and over again. And the language will keep coming up with values for you. So the only thing that ends up being a problem for when it came to Hammer was actually recursion, believe it or not, defining recursive parse rules. Let's say that you had a rule like for, I don't know, let's say pairs of parentheses, right? Open paren, close paren. So sorry, it's kind of late. If you have to use the rule itself, in the definition of the rule, how do you evaluate it before it's actually been, before enough of it exists to evaluate? It's like, what you can do in C is you can declare before you define. So we have some tricks for basically declare the thing that's going to recurse, declare the shape of that, and then insert the actual recursive part into it in the next step. So you have the variable available to reference, and then you use it, and then you use it once you can actually populate it. Another big problem for C, Tony Hoare's billion-dollar mistake. Most functional languages typically don't have null pointers at all, and the problem with them in C is that they really end up meaning undefined behavior. So, kind of the same way that we said, okay, we don't have a strong type system, but we can make one up. If null doesn't actually mean anything to the compiler, it can still mean something to you. So just as we need to reason consistently about the types that we've created, we need to reason consistently about what null means. And ideally, if you're going to make that decision, you want to try and make it as consistent as possible throughout the code, so that people like maintaining it later, for instance, don't have to go, oh god, null means this thing in this context, and it means this other thing in this other context, and it means something else over here. 95% of the time that maintainer is going to be you 6 months later, so be nice to yourself and try not to try not to force yourself to do context dependent reasoning. So in practice, you also have to add lots and lots and lots and lots and lots of null checks. Like, the entire code base is just salted and peppered with them. C also does not have garbage collection, and you have to clean up memory that you allocate somehow, otherwise it's going to leak all over the place. We didn't want to deal with trying to track track memory throughout the heap, because there's a lot of memory getting allocated on the heap here. So instead of just using the system allocator, we wrote our own. It's an arena allocator. If any of you have read if any of you have read Carmack's book on Doom, it's basically the arena allocator from that. It carves off a slab of memory for the context of each parse, and then when you no longer need that parse result anymore, you blow away that entire chunk of memory. And similarly, if as other parses are going on around you, they get handed their own little chunks of memory, and it all gets cleaned up at once when you're done with that parse result. Method dispatch. This is kind of an interesting problem for C, right? Because C doesn't have objects; it just has structs, and see, you have functions, but you don't have methods. But you can fake it with vtables, and we'll see a bunch of those later. Vtables are how C++ does objects, and nothing is stopping you from writing one yourself. All right. So with all of those preliminaries finally out of the way, let's take a look at some of the internals of Hammer itself. Okay. So we wrote a combinatoric front end for it. It has 6 different backends that you can choose from. I mean, LR0 is not really accessible from the interface, but you can use it if you really desperately need to. So part of what this means here is that you can avoid giving computational power to an adversary as long as your language is weak enough. If you have, for instance, a regular input language, you don't need to use all of the computational power of say LALR or a Packrat Parser in order to interpret it. You can use a backend that is exactly the computational power that you need. And this basically just reduces risk once the code is actually deployed someplace. We also wrote as many language bindings as we had time for, basically. I think at this point it includes C++, Java, Ruby, Python, Perl, PHP. I think that's it. I don't think we ever got around to Lua. And I did get it to compile under Inscripten, but I can't figure out how you're supposed to use the results of Inscripten as a library. So, like, JavaScript notionally out there, but I can't figure out what to do with it. And it's multi-platform. We started building it on Linux, but we also distribute for OS X. You can get it through Homebrew. And there is even a working Windows build, thanks to a very, very nice contributor named Nicholas. Okay. If you're going to be looking through the code, it helps to know what our naming conventions are, and they're pretty straightforward. If it's in camel case and starts with a capital H, it's a type. If it starts with a lowercase h and an underscore and uses more underscores, that's going to be a function. And we adopted this convention mainly just to make the code easier to read. So here's a simple, very, very high-level example with a parser that we're not actually like filling out the details of, right? So this function here, which you see referenced there, is a semantic action, and we'll talk about what that means in just a little bit. So here we're creating a parser that applies a semantic action to the result of whatever parser goes there. You call the hparse function on with the parser and whatever data you want to parse. You have some kind of struct that you built. You do something with it, and you're done. Okay, so what's inside a parser? Well, the very first thing inside a parser is a vtable, which is going. We'll get a closer look at some of those in just a little bit. It will also have a backend assigned to it, and that defaults to Packrat, but you can. But it's just one function call to set that to some other backend. Backend data and environment. These are basically just void pointers that we shove things into when we need to. The environment pointer might have something to do with what the parser is matching, like if the parser is matching like a specific character or a specific token, it'll get shoved into that one. And then backend data is for backends like LALR and LLK, that ends up containing some generated data that the parser uses internally, and you don't actually have to care how it works. Desugared is also kind of in the same boat as backend data and environment. You never have to look at it yourself, but it's a transformation of a structure of combinators into a we call it a sum of products representation. Basically, it's a choice between sequences that can also include choices and other sequences, and some of the backends use this, others don't. Okay. So what kinds of functions do we have? Well, I mentioned semantic actions earlier, and this is the prototype for a semantic action. Once you've got a parse result, once you have a parse result, it's going to be in the shape of a tree. An abstract syntax tree, specifically, which is what AST stands for. And so a semantic action transforms that tree into something else, however you decide to define that. So we also have this this class of attribute validation functions. This is another prototype for predicate functions. Similar to semantic action, a predicate takes some abstract syntax tree and checks whether some property of it is true. That might be something like, I don't know, the payload length is less than some value or whatever. Again, you can define it any way you want. And if that attribute validation function fails, then the parse also fails. And then the other function type that you'll see occasionally, particularly when you're composing several grammars together into a larger grammar for a protocol stack, is a continuation. This is in like the scheme call with current continuation sense. Once you call the first parser, you take its result, you hand that to the next parser in the chain. You take the result of that, you hand that to the next parser in the chain. You'll have these continuation functions to characterize how that happens. Okay, so as I said earlier, a parse result is the abstract syntax tree of parse tokens. It also gives you some metadata like how many bits did we parse. And it also gives you it also points you to the memory context, the arena allocated block of memory, so that you can throw it away when you're done. The parse tokens that are in the abstract syntax tree, we define some simple types for those. You can have a byte string, a signed integer, an unsigned integer, a sequence of anything. Or you can also define your own token types at runtime. So it's basically a tagged union, and you can add things to the tagged union. Excuse me. And each token will also contain a reference to where in the stream of input was it when we parsed it, both like what byte was it, and if there was an offset into the byte, how many bits was it offset in. Okay, so finally, we've made it to some actual parser combinators. So these are all primitive parser combinators. They parse concrete things. The simplest one is CH, the character parser. You tell it, match this character. Whatever argument you give it, it will match that character. H token is exactly like that, but for tokens that are longer than a single character. You can also parse anything in a range of characters. This is basically syntactic sugar to make that easier. Lower bound, upper bound are the arguments, and you can even say, I mean, there's also an in that will, so like if you can give it a set of characters and say, all right, except if the character is in this set or if it's not in the set. We've also got ones for integers, unsigned and signed, from 8-bit all the way up to 64-bit. If you need to parse some non-byte aligned number of bits, there's also there's a combinator for doing exactly that. Or you can match integers within a range. And finally, end of input. That's also handy to be able to recognize when that's happened. But these primitives are not super useful by themselves. You need to be able to combine them in order to be able to do something interesting. So I mentioned the sum of products representation before. That's what sequence and choice are. And H sequence, you basically give it a list of parsers, and it will apply each of them in sequence. And if they all succeed on the input, then H sequence succeeds. If any one of them fails, then H sequence fails. H choice, about like it sounds, you have some number of parsers to choose from. It tries applying them in order, And if any one of them succeeds, then the choice succeeds. Okay. You can also repeat things, kind of like in ABNF, the way that you write grammars for RFCs. You know, ABNF has like star for repeat 0 or more times, or plus for repeat one or more times, or you know, you can, there's numeric notation for some number of repetitions. So we've got that too. The question mark in ABNF means optional. So if you know, if a particular field in what you're trying to parse doesn't have to be there, you can just wrap the parser for the thing you want to match in H optional, and now it has that behavior. If there are things that you know are going to be in the input, but you also know that you don't care about their values, like padding bytes, for example. Hignore is you know, makes your resulting parse tree tidier and easier to reason about. And we've also got some higher order ways to combine primitives. For instance, length value, which shows up a whole lot, takes 2 parsers as its arguments. The first one is the parser that you use to parse the length. So it's usually going to be like HUint8 or something like that. You know, if the length is specified by a single byte, then it would be uint8, et cetera, et cetera. And then so what length value does is it applies the length parser, figures out, okay, what is the, you know, how many times do I need to successfully apply the second parser in order for the entire combinator to succeed. So like and not are basically conditional acceptance or conditional rejection. And I mentioned forward declaration earlier. H indirect and H bind indirect are where this come up. So if you have to define a recursive rule, then you define then you can define an empty H indirect and then bind it to and then bind it to itself later. Okay, I mentioned predicates earlier. This is how you use them. H adder bool is itself a combinator, and so the result of this is going to be a parser that, assuming that this parser succeeds, it will then apply this predicate to the result of that parser. And if that predicate succeeds, the whole thing succeeds, otherwise it fails. Similarly, semantic actions, they do all the parsing, then they apply the action, and if the action fails, then so does the parse. And then bind is where we use the continuations that you saw earlier. I mentioned endianness. Yes, you can change endianness on the fly, and TIFF is the reason that we had to do this. I really hope you never have to implement something that uses this, but it's there if you need it. We also put a symbol table in there because we had to, because we were working on a really terrible protocol called DNP3, which is used in industrial control systems. And DNP3 has a lot of long-distance and even cross-layer dependencies, where, like, a value like over on one side of the parse tree and a value somewhere hell and gone on the other side of the parse tree in a completely different context need to correspond in some way. So the least terrible way to do that, basically, was to build in a way to stash named values in a symbol table and pull them out and look at them later. Okay, so let's take a look at a small example from that you can actually find in the examples directory in the Hammer source code. So this is a very high-level overview of DNS. A DNS message is, let's start with just this part here. It's a sequence starting with a DNS header, and if you look in the if you look at the example in the source code, you'll see how the DNS header parser is expanded. You have 0 or more questions, 0 or more resources, and then end of message. End of input. The null is there because that's how var args work. C is terrible. But you'll notice that we've also got a predicate and an action going on here. So there's some validation that needs to be done for DNS as well. Like you need to make sure that the number of resource records matches up with the value that you expected and everything. And then once that validation passes, we have a semantic action that plucks all of the values that we actually care about, like the questions and the resource records. It pulls those out and packs those into a struct. And so we had to write an action to do that. Let's take a closer look at DNS questions. So what we've got here is this gets a little complicated because it's a sequence of sequences, right? Overall, I mean, it's the Q name, the Q type, and the Q class, right? But Q name is, Q name is itself fairly complicated. But we're able to simplify that by saying, okay, we know that we know that the Q name is going to be, its length will be specified by a value between 1 and 255. The reason we had to use int range here instead of just using uint8 as the length parser is because 0 is a valid 8-bit integer. But it's gonna pick up somewhere between 1 and 255 unsigned ints, octets, and then that'll be followed by a null byte. Similarly, resource records. There are parsers for domain, type, and class that we wrote according to the RFC. And we simply compose them into a sequence. There's also like the time to live, and then we're able to represent RD length and R data again using our friend the h-length value combinator. And we don't have to worry about like storing the 16-bit unsigned int. We just get however that many octets is as the payload. So let's take a closer look at validation. And this particular validation function kind of goes like a little above and beyond the Call of Duty. But the very first thing it does is, I mentioned that we define some of our own types using that tagged union, and if for some weird reason the result that you got somehow was something other than a sequence, the parse was wrong. So just bail out now. That shouldn't ever happen, but which is why that if clause is kind of overkill. But we've put it there for thoroughness. So we're able to decompose the elements that we want to check just by a long chain of dereferences, basically. And then we check to see, okay, well, is the number of questions that we got the same value as QD, this this ninth element in the elements that we parsed. And similarly, when you sum AN, AS, and AR, does that sum to the number of resource records? If it doesn't, then the validation function fails, and so does the rest of the parse along with it. Okay, so let's get up even farther under the hood and see what this is doing on the inside. So first of all, we're doing an awful lot of code generation. The combinators that you have available in the API are declared using this set of macros. So like we've got one macro to declare the no arg parsers like uint8. We've got another one for declaring that we've got others for declaring ones that do have arguments. We've even got a way to define we've even got ways to define things like sequence and choice that allow you to have as many arguments as you want. Okay, what does the input stream look like? You know, I mentioned the input stream before, and the fact that you're able to do things to it, like change the endianness around, or offset some number of bits into the byte and just keep parsing. Fundamentally, though, it's just a whole bunch of octets and a little bit of metadata to keep track of the state of those octets. So most of the functional style that we've been seeing so far has had to do with function composition. This is a little closer to the minimized state principle that we talked about earlier. All of the state of the input stream is localized to the input stream itself. There's not a bunch of other state changing elsewhere in the code. Being able to localize mutability helps you localize any side effects from that mutability. Okay, so what happens when you actually decide to parse something? Well, the hparse function that we saw earlier is basically a wrapper around this function, and this is implemented. What this does is first it initializes your input stream. Everything gets defined, you know, because you have to have it, because you want to know, like, you know, what is your known good ground state that you start from. So, you know, we've got default values for everything, and then it dispatches the proper parsing function for the backend that you're actually using. We have, like, there's a static table of defined backends, and we dereference through that. Okay, so suppose that we're using the Packrat backend. That's the one that can handle context-sensitive grammars. The vtable for it has three functions, one of which is a no-op, and all of the different backend vtables have these same three functions. We have the compile step for LALR and LLK and regex. We don't actually need it for Packrat. And then, you know, parse obviously does the parsing for, you know, in a backend specific way, and frees up allocated memory. Okay, so what's going on here? You'll notice that basically the first thing we do when we start a parse is we allocate a new arena for it, and then we've got some boilerplate here for what happens if there's an out-of-memory error. And this code actually arrived fairly late, and there's a funny story about why, which you'll get to hear in a couple of minutes. and this is actually kind of compressed from what it is in the original code for readability purposes. But again, set up the arena, set up what we do if an exceptional event occurs, and then set up the parse state. There's some more setup that has been eluded here. Do the parse itself, tear down the results. Tear down all of the the intermediate stuff that got used. If the result failed, blow away the memory immediately, and if it succeeded, return it. So what happens in the context-free case? Well, in the context-free case, we do actually have to compile things because LLK needs some additional data to operate two sets, basically. They're called first and follow sets. And LALR needs some parse tables. But before we can even generate those, we have to take the combinatoric parser that we wrote and translate it into that sum of products representation that I talked about. So the compile function takes care of that. Yeah, I just said. Okay, yeah. But yeah, basically you start at the top of the parser you've constructed, the highest level the highest level entity in that, and then you just walk down it, transforming the combinators into choices or sequences, as the case may be, as you walk through the tree. Once you have that, then you can then the backend can do its generation step, and then it stuffs it into that void pointer that we saw earlier. That's probably the dirtiest part of all of this, the fact that we're just using void pointers, because what else are you going to do? Similarly, if it's a regular language, there's a reason it's called the Thompson regular expression VM. It actually has an instruction set, and so the desugaring step for the regular languages translates the combinators into instructions for the regex VM instead, and then stores the instruction list in the backend data pointer. And this is what compilers do. Compilers take source code, and in this case, our source is a structure built out of combinators, and it transforms that deterministically into a set of instructions. However, I've kind of skipped a step here, because I didn't tell you how we figure out whether a parser is regular or whether a parser is context-free, or whether we have to use Packrat for it. What happens, for instance, if you try to if you have a grammar with recursive rules in it, and you try to compile that into regex VM instructions? Well, we kind of cheated. If you can't introspect on it, you can at least say it out. You can at least say it explicitly. So each parser, as it turns out, has its own vtable. Each of those primitives that we saw earlier, each of the higher order combinators, each of them has a vtable much like this, and this is the vtable for the character parser. So for historical bad naming reasons, the .parse function is actually how do you parse a single character in Packrat, or how do you parse a sequence of things in Packrat, et cetera, et cetera, et cetera. But what we've got here are we're just straight up saying in the vtable, is this valid to use in a regular grammar? Is this valid to use in a context-free grammar? And then desugar is for transforming into the sum of products representation. When you're walking the tree, you're basically starting with the root node, saying, okay, desugar me all right, desugar my left child, desugar my left child's left child, et cetera, et cetera, et cetera, until you've invoked desugar on every node in the in the tree of combinators. Here's the one for many. Again, like that's the Packrat function for 0 or more. You don't know, however, off the top of your head, just from looking at it, whether something that uses the 0 or more higher order combinator is going to be acceptable in a regular language or in a context-free language, unless you know what you're parsing 0 or more of. So in this case, the many combinator has functions is valid, many underscore is valid regular and many underscore is valid CF. Those get invoked on whatever arguments you handed to H many. It identifies, okay, are these okay to use in the kind of backend you want to use? And if it's not, then it'll error out when it examines it. And then we have other kinds of, there are other combinators that you just straight up can't use in anything weaker than Packrat. Length value is essentially inherently context sensitive because you're saying this many of that thing, and you have to count. You have to actually look at the semantics of the this many in order to know how many you're counting. So that's context sensitive. You can't do it in a context-free language or in a weaker in something weaker like regular. Okay. So I mentioned DNP3 earlier, the SCADA protocol. This is a very, very, very high-level and simplified diagram of what it looks like. So it's a 3-layer protocol stack with its own link layer frame format, its own transport format, and then its own set of application layer messages. And the specification for this runs to the hundreds and hundreds and hundreds of pages, mostly in prose and lots of really ugly tables. Like, there is no nicely written grammar for this, even though we were able to extract one. So it's messy. It's really, really messy. But this is kind of the core of it. You have an application request header. So in request, you'll have an application request header, and then that will be followed by 0 or more groups of an object header followed by 0 or more objects. Yeah, I don't know why it's not 1 or more, it's 0 or more. Thanks, industry. And the application header consists of a couple of fields. The object header consists of a couple of fields, and then the object consists of an optional prefix plus some object data. But things are actually worse than it looks, because what you just saw on the previous slide does not point out that, like, the flags from the app header and so the flags in the function code having a dependency, having cross dependencies, that doesn't matter quite so badly because they're right next to each other. They're adjacent in the structure that they belong to, and so you don't have to introduce too much more context in order to compare them. However, function code and the combination of group and variation, there's a semantic dependency between those, and those are part of those are part of different parts of what you're going to be parsing. So this is why we ended up having to introduce that symbol table, because of this stupid object header thing. You have to stash the function code from the app header, and then compare it to each of the group and variation pairs as you go through the packet. Similarly, it's these other guys also have semantic dependencies between them, and just the only way to deal with that was to say, okay, we need someplace that we can stash this value and compare it against things later. So yeah, that's why we had to add the symbol table, and it's terrible. Okay, but does it actually work in practice? So the person who actually implemented the DNP3 parser is a guy named Sven Hallberg, Pesco. He's based in Hamburg. He's usually at CCC. Buy him a beer for doing this, because my God, the man needs it after going through that mess that we saw 2 slides back. But so he finished it, and then he was like, all right, I need to test this somehow. You know, I've tested it on plenty of good data, so let's try throwing some bad data at it. And so he took American Fuzzy Lop and you know, AFL compile time instruments your code, and then uses genetic algorithms to try to come up with malicious data that will make it crash or do something else horrible. And it's been incredibly successful at finding bugs in very well-known projects. So, anybody want to hazard a guess as to how many bugs AFL found in the DNP3 implementation that we did in Hammer? It was not 0. It was 1. That set jump that we saw earlier, the exception handling thing, that was an out-of-memory condition. So, exceptions, as it turns out, are partial functions. Way back at the beginning, we were talking about totality. Partiality is basically the opposite of totality. You don't have an answer, you have a state that you can continue from, and if you have no way to continue from that state, then rocks fall, everything dies. So we had to, the thing that we had to do in context to handle the exception was clean up the resources that that got allocated but now no longer can be used, and all of a sudden we're back in the land of total functions again. Okay, so I have to hurry up and finish this, but let's talk about some other things. So, anybody here speak Rust? Yeah, all right. If you're using Rust, I highly recommend you take a look at NOM. NOM is written using the Rust macro system, which is just absolutely stone brilliant. You know, because Hammer is a bunch of structs all pushed together at runtime, and we've basically got an interpreter function that goes and interprets them. It is actually kind of slow, even for C. So what Jeff Kupri, who the author of NOM, did was he was like, okay, Rust has hygienic macros. That means that I can write my combinators as macros, and then when somebody when somebody writes a parser using these macros, the compiler will expand the macros into Rust code, compile the Rust code, and then there will be an insanely fast recursive descent parser that is also zero copy. So you end up with like just incredibly fast, incredibly lightweight parsers. I definitely recommend checking it out. Pesco also did another horrible trick. So there's this thing in Haskell called iteratees that basically it's a way to do operations on streams in a composable fashion. You know, what do you do if you have input that could possibly be infinite, and you know, valid things will come through as you go, basically. So kind of the dual of an iteratee is this thing called an enumeratee. It's either going to present you some data, or it's going to say there's not any more data yet, or it's going to say there will never be any more data ever. And the iteratee returns either stop and some return value, or continue and some information about how to do it, or if for some reason things have entered an inconsistent state, it errors. So like, suppose that you're dealing with like XML, right? And there might be there might be multiple encodings you have to deal with. Well, you can compose iterates such that the first one then dispatches to whatever the appropriate next one is. So he tried implementing word count with it, and it turns out to be faster using the iterate approach in C than it is out of the box. Okay, so we're finally done here. What I hope that you can take away from this talk is, even if the tooling that you have to work with is terrible, you can still work around that and set better standards for yourself than the tools that you have provide for you. You can do better than C. You can be a bigger person than C is. The compiler works very, very hard, and it doesn't complain that much, all things considered, but you are still smarter than your compiler. So as long as you don't confuse yourself, you can reason about things that your compiler doesn't know how to reason about, and leverage the compiler's diligence and your own intelligence to produce something that's greater than the sum of its parts. All right, so what are we going to do after this? There are lots and lots and lots of formats that need to get implemented in some kind of rigorous way. I mentioned very early on, I mentioned X509, right? Back in 2010, Len Sassaman and Dan Kaminsky and I were able to forge SSL certificates by playing stupid grammar tricks with X509, sending ever so slightly grammatically incorrect, or even just grammatically correct but semantically weird certificate signing requests to CAs. And because the CA was using an X509 implementation that was implemented slightly differently from, say, the browser's implementation, like OpenSSL versus, say, Crypto API, we were able to take advantage of very small differences in semantic interpretation and generate get validly signed certificates that should not ever have been accepted and that looked to a browser like a valid cert for high value sites. The NOM community is already starting to take that on for Rust. I hear rumors that there will be NOM code getting into VLC fairly soon for dealing with video formats. Bless that man. We'd like to improve the way that we deal with input streams. I mean, right now it's just octet based, but we have plans to come up with a way to do incremental parsing, like consuming data that's just constantly coming in on the wire. We'll probably take some inspiration from how iterates do it. The error reporting in Hammer is kind of awful. I don't know anybody who actually enjoys doing error handling, but we do need to make that nicer for users. There was a very recent and very exciting result in the world of parsing. So it turns out there's this really mathematically simple but kind of difficult to explain if you're not a mathematician approach called parsing with derivatives. And there was a recent result where it turns out that for the context-free languages, parsing with derivatives is cubic in time complexity with a very small constant. So it is now the best thing going for context-free languages, and we're working on getting that into Hammer as fast as we can. I have some stupid LLVM tricks planned. I mentioned how, Hammer is effectively interpreted. Well, LLVM does this neat thing where, literally everything the compiler can do has an API call available. So we can just JIT parsers. I've been working on this for a couple of months, and it's not very fun to debug stuff to debug something that was JITted and is now seg faulting, but we'll figure it out. And finally, it's time to retire C. We need to put that dog to bed. All right. Any questions?
I don't know the reason. I don't know the reason why loop has to be recursive instead of loop having a recursive function.
Well, I mean, you're talking about in the functional idiom, or
when you mentioned at the beginning that instead of having infinite list and loops, it's better having.
Yeah. So I mean, where you have for loops and while loops in functional languages, in procedural languages, you have recursion in functional languages. So the reason for that actually in the functional languages is referential transparency. If you're for I equals 0 to 10, right? That counter variable is mutable. And in a proper functional language with referential transparency, you wouldn't have that at all. Like you wouldn't be able to update the counter variable, and so since you don't have it, you use recursion instead.
At the beginning of the talk, you said that for certain context-free languages, there are some inputs that require totally more than other to be parsed, and so couldn't they be used to, do a DOS to this service to Hammer, or do you handle that? Is it possible to predict that?
Okay. So you're talking about like if you're talking about like if something has a pathological case. Yeah, unfortunately, that's something that the only really practical way to find it out is really thorough testing. My best advice for that is to use is to use test generation, like test case generation. Haskell gives you stuff like quick check, which literally just looks at the type signatures of everything in your program and generates input that matches those types, but that it hopes will throw your program for a loop. Hypothesis, I guess, MJ Dominus's tool. That's the only example I can think of for test case generation for like non-functional languages, but it's a good one.
I have to admit that I lost part of the talk, so if you already answered that during the talk, tell me to fuck off, no problem.
I'm nicer than that.
Why C? I mean, why not a safer language?
Honestly, part of it was just sort of to prove that we could. A sufficiently stubborn programmer can write Haskell in any language.
When you mentioned other language bindings, Rust was not there.
No, because somebody actually, there were a couple of contributors who started, and this was back when Rust was still at like 0.8 and it didn't have union types yet, and so yeah. But honestly, at this point, like now that nom exists, why bother? Just use nom. Okay. Nom is better in basically all possible ways.
All right, thank you.
Thank you, everybody.